Hello, everyone. My name is Elena Murchikova, and I am at the Institute for Advanced Study working in astrophysics. The goals of my talk today will be twofold. First, I'd like to give you an overview of black hole physics in the Galactic Center, astrophysical black hole, supermassive black hole, and why the Galactic Center black hole is our best hope to study and really see effects of general relativity close to home. And the second part of the talk, and they're kind of going to be slightly intertwined, is that I'd like to talk to you a little bit about how the problems in astrophysics are perhaps different from those you're used to in math or high energy physics. I believe I'm the only astrophysicist here, so I'll feel like I have to comment on this. Anyway, without further ado, let me first fly you to the Galactic Center. And by the way, if you have questions, please stop me in the middle of the talk. It's going to be so much easier than flipping through the slides back. All right, if you look at the sky in a dark moonless night, you see a bright stripe going across it. This is a Milky Way. You're looking at the edge of our own galaxy. Its brightest part is usually visible mostly from the southern hemisphere. This is where Galactic Center is located. So there is just more stars, more things. So visible mostly from the southern hemisphere, located in the constellation of Sagittarius, from where it takes its name, covered with a thick dust clouds, right on the side of this structure called mini-spiral, there exists the bright radio source called Sagittarius A star, which is the Galactic Center black hole. How do we know it's a black hole and why this black hole is important? Well, it is located about 8 kiloparsecs away from us, and the parsec in the upper right corner is about 10 to the 18 centimeters. The mass of the black hole is 10 to the 6 solar masses. And because of that, it's big enough on the sky for us with current technology to be able to resolve it up to the few Schwarzschild radii. Meaning that we can get information about the structures surrounding it and behavior up to the scale of few Schwarzschild radii. Well, how do we know it's a black hole? Well, this information comes primarily from tracking of stars in the Galactic Center. I'm going to show you two videos, and I'd like to point out that those are not simulations or toy models, those are real data. That's exactly what you see in the Galactic Center. The star here is the black hole, the dots are the stars, the closest group of stars to the Galactic Center. The data was collected meticulously over about 25 years since technologically it became possible. And some of the stars we see, especially this one, SO2, which orbit you see right now on your screen, is the one which completed almost 2 full orbits during the time of the observations. SO2 star approaches the Galactic Center black hole at about 1,000 Schwarzschild radii and passes by it with the speed about half the speed of light. Of course, I'm currently showed you just few stars which are passing the closest, but all of the stars are monitored, at least all of those we can see, meaning that the most information comes from those which are passing the closest because we see them moving over a span of months. But those which are further move slower, and they add less information to constraining the property of the object, which forces them to move this way. Let me show you another video, which is also observational data. It's from the nearest by time passage of S2 or SO2 star to the Galactic Center. So you can see that there is a huge mass forcing the star curving this orbit this way. This mass is so small, which we know from the distance to which the star approaches this mass, and so large that it can be nothing but a black hole. So black hole at the center of our galaxy is the kind of first proven black hole. And that's research, and the tracking of the star was a large part of the Nobel Prize, which was awarded this year, is for this research. Well, we have a black hole. We have a black hole which is we can resolve, which is the closest supermassive black hole to us, larger in the sky. Should we just start studying all the properties of, testing general relativity, seeing Hawking radiation, seeing objects redshifting when they approach in the galactic center? After all, we have a black hole in our possession. Well, the problem here is that we would love to do all of these things, except there is a little issue that the astrophysical black holes do not exist in the vacuum. They're surrounded by stuff, junk, gas, dust. This stuff is falling into the black hole and creating a background. And if you want to study space and time and find effects of general relativity, testing general relativity, deviation from general relativity, looking for some interesting effects, first you need to filter out stuff which is affecting your view. So what are we going to do? I'm going to show you how the close neighborhood of the galactic center black hole looks like. And close and astrophysical, by astrophysical standards, close like what? We have nearest star to our sun is Alpha Centauri. So I'm going to show you the region of about the radius of which about equal to the distance from the sun to Alpha Centauri. I'll keep this red arrow at the top of the screen and show you what actually is in the galactic center and what you have to take into account if you want to study fine effect of general relativity. How bad could it be? Well, anyway, I'm just showing this for the scale because remember the star I showed you was the full orbit, was the motions of the stars, which passes the closest to the galactic center. So up on scale, here I draw a circle and I zoom into this circle, and there is on the left on the screen, you can see the orbit of this S-orbital star. Anyway, so what do we have on the galactic center, which we need to filter out as junk? We have a nuclear star cluster, which contains about 1 million stars. And in case you wonder, yes, they are also tracked. In this image, you can see a part of the nuclear star cluster. And if I zoom in, you'll see this little blue arrows going everywhere. Those are the motions of those stars over the time of observations. So you can't see all of the stars because some of them are just smaller and fainter, but you can see the bright one, the big one, and they are all tracked. If you can separate it, you track it. Well, anyway, within this nuclear star cluster, it extends to about 1 parsec. Up to 0.3 parsecs, you see Keplerian follow-off radius. It's at the radius at which gravity of the black hole starts dominating the motion of the star. Away from this radius, it's star cluster plus the black hole. This is the plane of the galaxy. I'm showing you things on the standard astrophysical coordinates array index. So that's how plane of the galaxy goes in those coordinates. Here's the structure called mini spiral. These are 3 streams of the gas carrying the material toward the galactic center. The temperatures of the material is between 1000 Kelvin to 10,000 Kelvin. For the context, the sun temperature is 6,000 Kelvin. Here's, by the way, again, another image of the mini spiral. It looks pretty, very pretty. Well, next one. Here is circumnuclear disk surrounding the galactic center at about 2 parsec. Its second name is molecular ring, which gives you an idea that there are molecules there, meaning it's pretty cold. And when I say pretty cold here, I mean from few Kelvin, which is very cold, to about 500 Kelvin. Again, for the context, room temperature is 300 Kelvin. Here is the picture of the molecular ring. Anyway, next one. There's a clockwise stellar system, which is, I'm going to mention later. Its claim to fame is that it contains most of the Wolf-Rayet stars. Wolf-Rayet stars are the type of stars which are shading a lot of materials and blowing it away with the strong winds. So that's a powerhouse of creating winds all around the galactic center. All right, here's the remnant of an old jet. At some point in its life, Galactic Center was very active and even had a decent sized jet. It's hard a bit to see, and I would have pointed, but if I flip these images, you see that there is a line on this X-ray image, which overlined with the jet, which I marked. Anyway, next one. Now I'm going to zoom into the center. The circle I showed you, it wasn't a random circle. This is a so-called Bondi radius. The Bondi radius is the radius at which thermal energy of a gas is no longer enough to overcome the gravity of the black hole. Meaning, from X-ray observations, we can figure out the temperature of the gas and its density. From the temperature of the gas, we obviously know the velocities. Knowing the velocity, we know is it is similar to escape velocities from the black hole. And everything within the Bondi radius cannot escape and bound to fall into the black hole at some point. And again, for the context, I show this orbit of SO2 star, which I showed you before. Well, anyway, it's all very complicated, and clearly we can't just use pen and paper and try to reproduce it. We can't even use simulation to reproduce it because there are so many scales involved. What we're going to concentrate is the small region, just basically that for the time being. We're going to just talk about what's going on inside this Bondi radius. And again, that's the radius where your gas is bound to fall into the black hole. Of course, it's important what happens outside because it's initial condition, what's falling into the Bondi radius, but let's forget about it for a moment. We're concentrating on the innermost region around the black hole. Our goal is to understand how material falls and what sort of background it creates, because we want to remove it. And our big goal, we want to study space and time. Okay. So if you Google black hole accretion, you'll get the pictures like this. This is an artistic impression of the accretion of the black hole. You see a jet, you see some material swirling around, forming a disk, a pretty thin disk. If we remember that general relativity is also important, we understand that that's picture not going to look this way, but more like this, because you above and below the black hole, you see the two pictures of the disk, what was behind it. And we see lots of structures like this in the universe. For example, here is Saturn, and yes, the Saturn rings is just an accretion disk because there is debris, dust, and stuff. They form this disk, they collide and they rain into Saturn around the equator. Another famous example of the similar disk, which is also observation. This is the star which was recently born from a big cloud which collapsed. The star formed in the middle. Around it, you see a disk, which is debris disk, which is still there. The star hasn't blown it away. Material settles in this thin-ish disk, and inside this disk, you start seeing the collapses. That's where your planets are born. They are collapsing and start eating the rings around the planet. and growing. So you see the rings of future potential planets. Anyway, how do we get to this thin disk, the pictures like this? So the physics involved is being solved back in the 70s. And what mechanism in play here is that you have material, you have gas clouds, dust stuff. It starts falling into the black hole, it collides with each other. Its gain protons receive most of the energy from the falling into the potential well because they're 1,000 times more massive than electrons. Electrons at the same time collide with protons, exchange energy, gain the same temperature as protons. It's hot, they radiate, they cool, they interact with protons, they cool protons, the stuff settles. You don't have this puffiness because puffiness comes from the random velocities, and you're losing random velocity from this interaction. And that's how you end up with disks, thin disks around objects. So if we apply this approach to our own galactic center, because sure enough, it's our own, so we should know how it works, right? So we, from X-ray observation, we know how much material is within Bondi radius bound to fall into the black hole. We can estimate how fast this material is falling, meaning how much of material black hole eats a year. From this, which has been, we can estimate how much radiation we expect from this material while it is falling. And it's also been solved in 1973, and Tor Novikov. This sort of system radiates between 6 to 42% of mc square of material falling in, just in this process. And this 6 to 42% escape as radiation, and that's how we determine how massive the objects are, how much they eat. So if we do this calculation, then it turns out that from the amount of material Sagittarius seemingly eating, which is about 3×10⁻⁶ solar masses a year, it's supposed to be radiating about 10⁻⁴1 ergs per second. Observation, however, show us that it's radiating about 10⁵ times less. So that's a little issue, you might say. Well, the problem is with the previous model, which I described to you with the thin disk, is that it requires a lot of interaction. It requires thermalization, that electrons and protons exchange energy and then thermalize, they have the same energy. What if your flow is so thin that protons just don't meet electrons very often? There is not enough interaction there. And as a result, protons stay much hotter than electrons. Electrons are much cooler. They primarily responsible for radiation, and they just can't radiate the energy which they don't have. So the flow seems to be much cooler than it actually is, because it drives more material in than what would we expect from the amount of radiation it produces. Well, this is just a picture, right? How exactly does this flow work? Well, does everything in this very thick puffy structure, and then because it can't cool, so it stays puffy, and not just puffy, it just like fills most of the space and just kind of you can hardly even call this disk, because it just fills a lot of everything. So how does the exactly physics inside the structure work? Does everything is moving into the black hole? Does it have some outflows? Does it contain some things like convection, like when you have coffee cups and everything, and then this stuff moves? Turns out, depends what mechanism you think are important for your accretion flow. You get vastly different prediction for the structure of this accretion flow. For example, density, and I mean number of particles per cubic centimeter, will vary, depends on your assumption, between scaling with radius as r minus 3/2 to r minus 1/2. And let me again give you a context. If I'm looking at 10 Schwarzschild radii, and I look at the 1,000 Schwarzschild radii, which are 100 times further, is the density of my accretion flow fell by 10 or by 1,000? That's a big difference. This is something you need to know if you want to understand it and want to, remove it and want to understand how the space and time works. So this is not an answered question. This is a work in progress, and that's in the field I'm personally work. That's what sort of questions people ask. How could you try to answer those questions? So there are obviously various approaches. We have to use a combination of those. First approach, one of the approaches, not first, just one of those, would be simulations. What you do? You take a truncated problem, toy model, you include the most important effects you think, you run it, and you put everything you know about what physics is important for this particular toy model. You run it, you look, compare with observation and see, does it look similar? If it looks similar, great. Now you extend your model to include more things, more structures, maybe things you know less about, and see what difference do they make. So you run your model, compare, repeat, and do it over and over again. Here's an example. So this is actually a state-of-art simulation of the Galactic Center where you start basically with just a black hole in the middle and a bunch of stars on this clockwise stellar system, which Wolf-Rayet stars, which blow in lots of winds. So how it looks, empty space, a bunch of stars there on the orbits, which we know. Stars start blowing winds. At some point, those winds start filling all your volume. And when everything settles to get to some steady state, then you can compare it with observations, make a mock observation and see, does what you see in your simulation look in any way similar to what you expect from what you see in observations. I showed you pictures from two different groups who are doing similar simulations. And what we're doing now, me and my colleagues, we're working on extending the previous model and to account for more structures in the Galactic Center. In particular, if previously Galactic Center looked like a black hole and a clockwise stellar system, we also want to include the circumnuclear disk and the mini spiral. Next one would be you do observations. And what I mean innovative, I mean you do something which hasn't been done before because it wasn't possible to do, or because you just came up with a new technique to analyze if you found new probes and new analysis techniques. So you try to use new instruments if they're available, and you invent new probes and you develop new analysis techniques, as I said. So here's an example of that sort of approach. We know that the most information about accretion on the Galactic Center coming from this image from X-ray observation on the left, upper left corner. This is X-ray observations. X-ray observations are wonderful, but the only thing they see is very, very hot gas. I again remind you that this image is about the same as the image in the bottom right, or about the same size as the image in the bottom right. You don't see any of the other structures because X-ray is also allows you to see gas which is very, very hot. But as you know, as I already told you, there are other things carrying a lot of other sort of gas, and this gas can also be contributing to accretion and maybe falling into the black hole. And we can try to study this. And we recently, with collaborators, discovered the disk of this colder gas well within Bondi radius of black hole in the innermost accretion parts of the accretion, where it's tracing the rotation of the bigger accretion flow. This observation was done on a wonderful telescope in Chile called ALMA. Well, anyway, this is just some examples. The work is ongoing, and there are conferences on the subjects, and we're just working to get the answers to these questions. Well, with this, I hope I managed to explain you a little bit of what astrophysics of Galactic Center black hole looks like. Let me now go to another topic, which I want to spend just a couple of minutes here. Okay, so it started from Young at some point asking me whether I can show some cute mathematical problem which astrophysicists can solve. And I remember thinking that, oh wait, but the field doesn't work this way. So I feel like first I need to apologize that no, I cannot show you a cute astrophysical problem which astrophysicists can solve. And let me now explain you why. Well, first of all, it's important to remember that astrophysics is at the stage when there is far more information coming from the sky that we're capable to process through, understand, and explain. Part of it is because technology is developing fast, and we're getting new instruments. The other part of this is that the finding in this field is disproportionately go to collecting data rather than thinking about it. Without regard that sometimes it takes much more time to think and explain something than to collect the data. Well, as a result, we use a lot of reasonable assumptions, ad hoc models, and power law scalings of not so clear origin. Because in most cases, we don't know the full list of effects which are important in describing our systems. They never isolated. They always many-body. And they live in the environments, in most cases, largely unreproducible on Earth. We can't just say, well, we can't figure this out. Let's see. Well, if I give you a structure of even pure metal and ask you, does this superconduct? You won't be able to tell me. But you can go to the lab and say, how about testing this? People can test and can tell you, well, we can't do that in astrophysics. So we use approximations which are all often not entirely correct, is sometimes known to be far from realistic, but they're still better to account for something than account for nothing. You can't, even if you don't know how certain things work, but you have general idea, it's better to use that than not using anything at all, even though you know your ideas is probably, or most likely, not how it works in reality. So in astrophysics, we don't have the problem of not being able to solve a problem of well-posed system of equation. So the problem we have is not being able to pose the problem. Because even if you write a system of equation, if an astrophysicist asks you how to solve the system, the first question you should ask, is that the system which needs to be solved, rather than how to solve the system. And with this, I'd like to thank you for your attention, and I'm looking forward for the questions. Thank you.
Thanks very much for a lovely talk. Are there questions?
Yeah, Vishnu, if I can ask.
Please.
I also wanted to thank you for a great talk. I am a theorist, and I personally find it great to be reminded of how how stupid it is, the problems that we are trying to understand compared to the real physics that you are doing. So thanks a lot. So I have a little bit of a very mild question, which may be very badly formulated. So sorry about that. But is there any hope of combining information from gravitational physics to learn something about astrophysics, or we are still very far away from that possibility?
Say it again. So you want to use information from which particular part of gravitational physics?
Yeah, well, I'm wondering. I mean, sorry. This may be, as I said, a very poorly defined question. But so for instance, in principle, my understanding is that using gravitational waves, and of course there is a lot of noise, and you know much better than me. But one would be able to probe, for instance, the mass of the black hole and things like that. So is there any communication between the different communities that are working in your area and in gravitational wave physics to try to see whether there is any novel way of extracting information from gravitational waves, or this is a completely poor direction to explore?
I think I get your question. So yes, of course, people use information from gravitational waves. It's a booming community, and they have this amazing observation and bring new information and new constraints. And just one of the most obvious things that you wouldn't expect, there are so many 30 solar massive black holes. Now, people was like, how on earth we're going to make those? Yes, absolutely. It's very, very useful in all the possible aspects, and more information comes from there. Well, not every day, whatever data releases, and this is advances community. If you're asking the question whether this can be in any way used to study supermassive black holes, then no, you can't. You can actually, we did some learning seminar where my job was to explain LIGO bands. You can do a very simple calculation, what sort of black hole LIGO can look at. So your main idea is, when things are started spiraling, it's need to be not so super long, but not so short that you won't be able to see it.
Right.
So basically you need a couple of oscillations, but all within like reasonable amount of time, because if it's decaying like for months, well, good luck to you, you're never going to see it.
Right.
So you will end up that LIGO is only for stellar sized black holes.
Yes, okay, I see. Right.
There are other proposals of other instruments. Well, until they fly or work, I would rather not comment, because things been around for a while. So no, you can't do anything with supermassive black holes. The advantage of, so why I was concentrating on supermassive black holes, like it's true that stellar black holes, we have stellar black holes closer to us than supermassive black holes. But if you look at the size, and as we all know, the radius scales proportionally with mass, stellar sized black holes are terribly small. If you make sun into a black hole, you get a kilometer.
Right.
Even at the location of Alpha Centauri, good luck to you finding it. While supermassive black holes, they're actually pretty sizable.
Yeah.
Within our, so well, obviously, if something is in our galaxy, it's the closest, and matter is not scale-free. Stars which are orbiting our galactic center are still the same stars which are orbiting M87.
Yes.
Sure, the size of the black hole of M87 is a bit bigger than our own, but matter is not scalable. I can't see individual stars around M87.
Yeah.
So if you want to really study things falling into the black hole, and you'd better do it with Sagittarius, because light crossing time is about 2 minutes. You can see things moving in your lifetime. When you look at M87, well, good luck to you to wait until it rotates 45 degrees.
Right.
We're
Of
kind of
course.
lucky to have something which, if we know it well, is a huge instrument which we would be able to use. Another comment is, sorry, I'm just getting more and more information that you didn't ask for, but maybe it also kind of answers your question. So gravitational wave physics heavily uses, the main thing they use is the waveforms. Two black holes collide.
Yeah.
I don't know how familiar with you are with the subject, but there is no analytics of this process whatsoever. At some point, it's been started. It's like, you cannot give me analytical solution. I'll take a point, terribly small black hole, but black hole, and throw it in much bigger black hole. You won't be able to give me waveforms of this analytically.
Well,
there is no studies of this. Everything which comes out of like have been using a computer. So there is no analytic of geometry dynamics at all.
Well, in fact, now that you mentioned this, there is a specific setup, which, of course, talking to you, you may, of course, argue that these things don't exist. But the part where I have worked a little bit is if you consider this last situation that you have mentioned, in which you have a very small black hole compared to a very big one. And then I don't work with the full GR machinery, but I work in the MRI approximation, in which I describe it as a geodesic, and I do perturbation theory.
Mm-hmm.
If the primary black hole is very close to extremality, there are some analytic results from our theoretical community.
I don't want to argue. It's like, yeah, but
this is very specific. I completely agree. Yeah.
And this is kind of sad, because here's your mathematical problems. This, if you look in the respectable paper on geometry dynamics, Wheeler, this is the one who is going to the one from Minzer to Wheeler. It's been a while, in my opinion.
It's been, no, I agree. No, we should be working more into real physics. I'm with you, but yes. No, okay. Thanks for your answer. Yeah, thanks a lot for your patience.
Thank you for the question.
All right, any other questions?
Just a hi, Elena. I really appreciate you making such an effort to make this, appealing to a mathematical audience. Thank you very much for a nice talk. This is more of a comment, really. I'm aware in the astrophysical community, there's a very active machine learning presence. I guess on two levels. One, of course, is astrophysical observation. All of my friends are doing, they're scanning sky maps and machine learning pattern recognition. But then there's another level, I think Tegmark and friends are doing it, which is sort of analytical regression analysis, which try to create laws in this astrophysics. Because I like your last two slides saying, there's this lack of analytic and lack of laws. And so do you have any comments about that approach towards this trying to uncover the underlying laws from the astrophysical observations?
Well, I might sound terrible, and
Sorry.
I might say something you might not like. Or
okay, yeah, please say whatever. Like. This is a dialogue.
I do believe that machine learning, this field, is incredibly good at marketing. Because the terms they use for incredibly simple things make them sound so incredibly brilliant. For God's sake, this is a linear approximation on steroids. If I can't, I do understand it's very important, because really it's not the way to go to say, we need a citizen science, tell us which direction this galaxy, I will show you the picture, which direction is it rotating, to the right or to the left? And then you learn things about psychology. People who are right-handed tend to see more right-handed things than those which are left-handed. That's not the way you go. We do need machine learning to classify things, but you cannot make a machine come up. You can't find, the patterns, because, you just physically can't look at the terabytes of the, LSST data, because you need to know some things. But machine, it's not intelligence, it's a linear approximation steroids. And if you as a human who knows all this physics, or who knows the law, who know how it works, I do understand like not being able to wrap your hand around that much information. But if you condense something, and if you can't do it as a human, how could you expect a machine to do it? Classification is amazing. I'm all up for it. But really, I think it's overhyped. Sorry.
No. It's interesting. Well, maybe you could come to the session tomorrow afternoon at this time, which is sort of like a small machine learning in fundamental physics session, and it'll be interesting. Thank you very much. Anyway.
Thank you so much for inviting. That's been a pleasure.
Of course.
Other questions? Well, let's thank the speaker, and let's thank all the speakers for the excellent session. So thanks to Diego, Joan, George, and Lena. And I'll hand it over to the organizers.
Well, thanks to Vishnu for organizing this, for chairing this session. So we'll resume. This is day 3 of 14. Take it away. Let's go crazy. Giorgio. It's 6 p.m. now here in the UK, which means it's beer time.
Okay, enjoy.
But of course that beer time in any time zone means beer time for everybody. That's the general rule.
Okay.
Sorry, I cannot come very early, but I always come the second session because
it's impossible. I mean, unless you're like Erdish, you're not gonna go stay for both morning and afternoon sessions. So far actually, Ed is probably keeping track of this. Has there been any person who has attended morning? And I think there's only been one person, is Hao Shank, for the first day. Or are there any more?
That was quite impressive. Yeah, it's definitely very early for anyone in the US.
So Hal is algebraic geometer. That already says a lot. But also he was a captain in the U.S. Army. He's a very interesting guy, dear friend of mine. So he woke up 4 a.m. to go to session number 1 and stayed for the entire length. It's U.S. time, so he stayed all the way till the end.
Wow.
This is probably why he's not here today. I think he's probably in hospital now or something.
Coffee overdose, probably.
Okay, see you tomorrow.
Awesome.
Everyone.
Thank you so much for everyone.
Thanks.
Thank you. See you in the morning.
Ciao. So we'll do that again.